But we discovered on our TI-84 calculator that we can bypass the factorial notation and we can just use the NPR function directly. Okay. If you're trying to form a permutation or a certain order of events where you have duplicates, then you have to resort to this second rule, if you will, for permutations. In which case we have to reduce the total number of ordered arrangements by dividing by the number of duplicates that do occur, so that we don't have redundancy. We then turn our attention to if order does not matter, and that would be the domain of the combination function. So if we have n things to select from, and we're going to select r things at a time, where order is unimportant, to determine the number of possible selections or arrangements, we would be speaking in terms of a combination. And the combination function, like the permutation function, involves the use of factorial notation. And it does have an extra factor appearing in the denominator, namely r factorial. Because of that, combinations are always less than permutations numerically. Okay. And we discovered also on our calculator we have an NCR function, so we don't have to use the factorial notation when computing combinations. So this basically summarizes all of the counting rules that we've investigated in section 4.4, fundamental counting principle, permutation, where all elements are unique, and then we have a permutation rule where we have duplicate elements, and then we have a combination function here where order does not matter. Okay. And again, on our calculator, we were able to find these functions with no problem. All right. So let's go in our textbook and see if we can do a couple more problems out of section 4.4, as I did not finish that section in its entirety. All righty. A couple problems I want to look at in this section here. Now, we did do a fair number of these problems already. Most of them were involving permutations, though. So okay, let's see. Okay. All right, let's look at problem like number 11 here. If 5 regular dice are rolled, how many different outcomes are possible when you roll 5 dice? Now, they want these outcomes to be different or unique, so they don't want any repeats here. So you could think of this, and order wouldn't matter here. All right. You could think of this as being like having 5 like mailboxes, or 5 slots, if you will, one for each die here. So this is die 1. All right. So die one, when we roll it, could yield 6 different outcomes. So event one, which is rolling die one, could occur 6 different ways. Now, one of the outcomes of these 6 for die one, when we roll it, we keep out. And that reduces the lot of unique outcomes on subsequent rolls down to 5. So when we roll die number 2, there are 5 possible outcomes times. So I am using the fundamental principle of counting. And by now, we've left out 2 outcomes, the outcome from die 1 and the outcome from die 2. And so now what we're going to try to do is figure out, well, how many outcomes are possible in slot number 3, where 2 outcomes have already been determined. It leaves us with 3 possible outcomes for rolling die 3 times. But now 3 outcomes have been predetermined, and we only have 2 unique outcomes left. So when we roll die 4, there's only 2 possible outcomes for that. And then die 5, we got it down to only 1 possible outcome left. Okay. All right, so this would represent the total number of different outcomes that could occur. And when we multiply these together, we get, let's see here. Let's see here. 1, 2, 3, 4, and 5. So we get 180. Different outcomes. Okay. Now, these problems down in here are going to give us a little bit of a workout with permutation notation and combination notation. And again, we could try a couple of these, like 14E here, 10 permuted 9 ways. And hit our math button, go over to probability. We go down and get the NPR function. So 10 permuted 9 ways would give you a large number, 3,628,800. Okay. So that's the NPR function. That's for a permutation there, where order doesn't matter. So that's saying if we have 10 things to select from, how many ways can we select 9 of the 10 things in a specific order? There would be this number of different ways here. Okay. And then we can contrast that with combinations here. This is combination notation. So like for number 33D, 10 in combination with 9. Then hit your math button, go over to probability, and grab your NCR function. 10 in combination with 9. That's going to give you a lot less possibilities here. Okay. And reason being is because order does not matter. So there's a lot less possibilities there with a combination. All right. Now, from 43 here, I'm going to have you try this one for classwork number 1, number 43. Selecting a committee. If there are 7 women and 5 men in a department, how many ways can a committee of 4 people be selected? How many ways can this committee be selected if there must be 2 men and 2 women on the committee? How many ways can this committee be selected if there must be at least 2 women on the committee? Okay. So there's actually this question here, this question here, and this question here. So there's 3 different questions here. All right. So I want you to, read and think it over and see if you can figure out whether this is going to be like a permutation or a combination, whether order matters or does not matter. And I mean, read this again. Does it seem like order matters or does not matter in this problem? If not, then you're going to be using a combination here for these problems here. Okay. So I'm going to have you just play around with that a little bit. We'll call that classwork number 1 or problem number 43 there. So go ahead, think about that and see if you can work that one. Okay, so let's take a look at this here. Again, there are 3 questions for this problem. And so there are 7 women and 5 men in a department. How many ways can a committee of 4 people be selected? All right. Now, it does not appear that order matters here, because there really is no distinction as to what type of benefits a person would receive if they're selected in a certain order. There's really nothing to mention here, so order does not matter. So we have how many people to select from totally? There's 12 people, and we're trying to put together a committee that has 4 people on it, where order does not matter. So for 43, so we'll call this 43 problem A, where order does not matter. So we have 12 people to select for, and we're trying to put together a committee of size 4. So this is just going to be a combination here. All right. Which if you want to use your factorial notation or the strict formula, it would be this here. Okay, so that's going to be 12 factorial, and that's going to be over 8 factorial, which is to say 12 times 11 times 10 times 9 times 8 factorial, and that's divided by 8 factorial. So 8 factorial drops out here, and we're left with 12 times 11 times 10 times 9. Which is going to be 11,880. Okay. Let's see here. Ways can a committee of 4 people be selected?
Don't you have to multiply the denominator by r factorial as well?
That is a combination, so that would be times 4 factorial also. Yeah. So we do have times 4 factorial, which is 4, it would be 24. So we got to divide this by 24 here. Yeah. Yeah, 495. So I was using the formula incorrectly there. Or again, you could just use the NCR function on your calculator. So there'd be 495 different ways of forming a committee of size 4 if we have 12 people to choose from, where order does not matter. All right, second question here. How many ways can this committee be selected if there must be 2 men and 2 women on the committee? Okay. 2 men and 2 women. All right. So we're going to try to put together a committee of size 4 where we have 2 men and 2 women. Now we have 7 women to choose from. So we're going to have 2 women on the committee and 2 men. So we have 7 women to choose from, and we want to select 2 where order does not matter. So the number of ways we can select 2 women from 7 women where order does not matter is going to be 7 combination with 2. And, okay, we also must select 2 men from 5 men where order does not matter. So the number of ways of selecting 2 men from 5 men where order does not matter would be 5 in combination with 2. So this is the number of ways of forming a committee of size 2. Notice that these numbers here add up to the size of our committee. All right. And we're using the fundamental principle of the counting principle here and multiplying these together. It's the number of way of selecting the women times the number of ways that the men can be selected. All right, so we're going to dial this up, and I'm just going to use my NCR function on my calculator. So n in combination with 2, that's going to give me 21. And then I'm gonna multiply that by 5 in combination with 2, which is 10. And so that's gonna give me 210. All right, so there will be 210 different committees of size 4 that we can form if we must have 2 women and 2 men on the committee. And again, the overall assumption here with this problem is that order does not matter. All right, it doesn't matter like in what order we select them in. All right. Anybody get that 210? All right, first, the third question, how many ways can this committee be selected if there must be at least 2 women on the committee? At least 2 women. And of course, our committee size is 4. And so this could occur in a couple of different ways of putting together this committee of size 4. We could select 2 women. Or we could select 3 women. Or we could select 4 women. This is to say a committee of size 4 where there must be at least 2 women on the committee. At least 2 means 2 or greater. Okay. All right, so how many different ways can we form a committee of size 4 where we have 2 women? Well, we have 7 women to choose from. And so the number of ways of selecting 2 women from 7 where order does not matter is going to be 7 in combination with 2 times. But if I select 2 women, I must select 2 men because my committee must be of size 4. And I have 5 men to choose from. So this is the number of ways of selecting 2 men from 5 men where order does not matter. It'd be 5 in combination with 2. So this is a way of putting together the number of different ways of forming a committee of size 4 where we have 2 women aboard. Okay. But there's also a possibility of selecting 3 women to form our committee. And how many different ways can we select without order meaning anything? 3 women from 7 women. Well, that's going to be 7 in combination with 3 times. But if I select 3 women to be on the committee, there is 1 more spot available for a man. And we have 5 men to choose from. So how many different ways can we choose 1 man from 5 men where order does not matter? This will be times 5 in combination with 1. So that's the number of ways of forming a committee of size 4 where we must have 3 women and 1 man. But there's another possibility. We could have 4 women on the committee. And how many different ways from 7 women can we choose 4 women where order does not matter? It's going to be 7 in combination with 4 times. But if we select 4 women, ladies and gentlemen, we don't need any man on the committee. There's no room left for anybody else on the committee. So this will be multiplied technically by the fact that we have 5 men and we're going to select 0 men from 5 men. 5 in combination with 0. Now, or suggest that we are to what? Add together things. And so therefore, we're going to add together all of these. All those must be added together. Now, the first one is going to give you 210. And how would you do that on your calculator? Well, I can show you how to do the first one on the calculator, and then you'll know how to do the other ones. So, all right. Okay, so I'm going to show you how to do the first one here. It's 7 in combination with 2, and I'm going to put it inside parentheses here. So 7, math, probability, NCR function, 7 in combination with 2. Bring your cursor back up to level, close parenthesis, times, open parenthesis, 5 in combination with 2. 5 math probability combination with 2. Close parenthesis. So there'd be 210. So there's 210 different ways of forming a committee of size 4 rather, where we have 2 women on the committee. Well, that's how I got 210 there. Everybody see how I did that? So it's a lot quicker without having to go through that factorial notation there. All right, now the next one is 7 in combination with 3 times 5 in combination with 1. And that gave me 175. When I put this on my calculator, I got 175. So there's 175 different ways of forming a committee of size 4, where 3 women must be on the committee and 1 man. Finally, how many different ways can we form a committee of size 4, where we must have 4 women on the committee and 0 men? When you work this out on your calculator, you'll get 35. Now, when you add all these together, you're going to have a sum of 420. And that would be your answer. So there's 420 different ways of forming a committee of size 4 if we must have at least 2 women on the committee. All righty. Did anybody get that there? 420?
Yep.
Okay. All right, so we'll call that classwork number 1. All right, that was number 43. All right, I'm going to have you play around with number 45 for classwork number 2. 45. We'll call this classwork 2. The Hawaiian alphabet consists of 7 consonants and 5 vowels. How many 3-letter words are possible if there are never 2 consonants together, and if a word must always end in a vowel? All right. What are the vowels in our English alphabet here? A, E, I, O, what? U? Is that correct? And sometimes, what is it? How does it go? And sometimes Y? Is that correct? So B is a consonant, C is a consonant. So notice they don't want any consonants together. So if you're trying to form a 3-letter word, ladies and gentlemen, you cannot have 2 consonants adjacent to each other. So this would not be legal. You cannot have a consonant and then a vowel. Notice the word must end in a vowel though. So you cannot have adjacent consonants. Okay. All right, so I'm going to let you think about that and see if we can enumerate a number of 3 different words we can form where we have to adhere to these restrictions here. Okay. All right, go ahead and play around with that. All right, let's take a look at this problem here now. It says the Hawaiian alphabet consists of 7 consonants and 5 vowels. How many 3-letter words are possible if there are never 2 consonants together? In other words, adjacent to each other, next to each other. And if a word must always end in a vowel. So because the 3-letter word has to end in a vowel, we're not really concerned with that spot. We are concerned, however, with the 2 other spots, or the 2 other slots, if you will, to form this 3-letter word. So we can look at this problem here, and we can think of it as being kind of like, again, like 3 slots here. So, all right. Now the letter has to end in a vowel. V for the word vowel. Okay, and we cannot have back-to-back or adjacent consonants. So we cannot have a consonant and a vowel. This is not accepted. Okay, can't have that. So letter must end in a vowel. So what we could have, however, is we could have a consonant and a vowel. Or we could have another possibility is we could form a 3-letter word with all 3 vowels. Or there's one other possibility. Remember, the word has to end in a vowel. This is a requirement. You got to have this. Or we could have a vowel and then a consonant and then a vowel. These are the only 3 possible options here for forming this 3-letter word. Because you cannot have consonants back or adjacent or next to each other. And the word has to end in a vowel. Has to. Okay. Well, so how would we, figure this out here? Well, to occupy the first slot, how many consonants are there? Well, there's 7 consonants, correct? All right, so 7 consonants could occupy the first slot. Times how many vowels could occupy the second slot? Well, there's 5 vowels. So 5 times 5, and there's 5 vowels to occupy the third slot. Okay. Or we could form a 3-letter word where we have all 3 vowels. And if that's the case there, there's 5 vowels, correct? And so there's 5 ways to occupy the first slot, and there's 5 ways to occupy the second slot, and 5 ways to occupy the third slot. Okay. All right, now the third possibility is a vowel, consonant, and a vowel. There's 5 vowels to occupy the first slot, 7 consonants to occupy the second slot, and 5 vowels to occupy the third slot. All right, so we just have to enumerate all these, and we're going to add them all together. So we're going to have 7 times 25, 175. 5 times 5 times 5 is going to be 125. And again, we're going to have 175 here. All right. So when we add these together, we get 475. So there's 475 3-letter words that we can form with the Hawaiian alphabet if we cannot have adjacent consonants, and the 3-letter word must end in a vowel. 475 different possible 3-letter words. Anybody get that too? Okay. All right, so all right. Next one is number 47. See if you can do this one here. And we'll call that classwork number 3, 47. How many ways can you pick 4 students from 10 students, 6 men and 4 women? If you must have an equal number of each gender, so you must have an equal number of each gender, or, notice, or all of the same gender. Okay, so go ahead, think about that and see if you can enumerate all the possible ways of satisfying these requirements here from what we have to work with. Okay. It does not look like order matters here. All right, there's a little hint. Okay, go ahead and do that one there, number 47. Okay, let's try to wrap our heads around this here. How many ways can you pick 4 students from 10 students? 6 who are men and 4 who are women. If you must have equal number of each gender or all the same gender. Okay. So, I mean, you could think of it as being like we're trying to form a committee of size 4 students. We have 10 to select from. Our committee must have equal number of each gender, or it must have all the same gender. Okay. Now that or is a little bit of a hint there to suggest that we're going to be adding things together, or always means adding. All right. So let's see if we can begin to put this together here. So we're going to form a committee of size 4 students where we could have an equal number of each gender here. Now, to have an equal number of each gender, we could have 2 men and 2 women. That's a possibility. Or, which means we're going to be adding. Or we could have all the same gender. We could have 4 men. Or we could have 4 women. Okay. So in general, this starts to give us an overview as to where we're going to go with this whole thing here. We could have a committee that has 2 men and 2 women, or 4 men, or 4 women. So if order does not matter, how can we form all these different committees here? Well, we have, what was it again? How many men, how many women? Let's see, there were 6 men and 4 women. Okay, so here we go. So how many different ways can I form, or excuse me, choose 2 men from 6 men if order doesn't matter? This is going to be 6 in combination with 2 times. How many different ways can I choose from 4 women, 2 women, where order does not matter? This is going to be 4 in combination with 2. All right. Plus, well, suppose I was to form a committee with all men on it. Well, how many ways can I, from 6 men, choose 4 men if order doesn't matter? That'd be 6 in combination with 4. Technically, it would then be times the fact that we have 4 women, but we're not going to choose any women. This is a way of putting together a committee of all men, 4 men. All right. Okay. So plus, now what if we wanted a committee with all women? Well, that means if we have 6 men, we're not going to choose any men. Times of our 4 women, how many different ways can I choose 4 women from 4 women where order does not matter? That'd be 4 in combination with 4. So there you go. This is going to give us our answer. We just need to, get on our calculator and dial all this up here. So let's see here. What is 6 in combination with 2 times 4 in combination with 2 give us? That gives us 90. All right, and then we got 6 in combination with 4. And now this guy is going to be 1. Okay. So that's going to be plus 15. Plus this is going to be 1. And this is going to be 4 in combination with 4. Would give us 1 also. So when you add all these together, you're going to end up with 106. So there's 106 different ways of forming a committee of 4 students, where either we must have equal gender on the committee, or we must have all 4 men or all 4 women. Okay, 106. All right, anybody get that? 106.
Yep.
Okay,
Yeah.
alrighty. Okay, that was classwork number 3. All right, try number 50 now. Last work 4. There are 16 seniors and 15 juniors in a particular social organization, and how many ways can 4 seniors and 2 juniors be chosen to participate in a charity event? Okay, go ahead and do that.
Apparently that's the answer. And that's for number 50. Yeah. Okay.
Okay, let's take a look here. We have 16 seniors, 15 juniors in a particular social organization, and how many different ways can 4 seniors and 2 juniors be chosen to participate in a charity event? And it does not appear that order matters here in how we select these juniors and seniors. There's no mention of, like if there's any office, like president or vice president or treasurer, that they'll hold if they're selected in a specific order. So we're not gonna assume that order matters here, so we're talking about combinations here. So for number 50, okay, so how are we gonna put this together here? Now, we need to select 4 seniors from 16 seniors. We need to select 2 juniors from 15 juniors. And so the number of ways that the first selection could be made would be 16 in combination with 4. That would be the number of ways of selecting 4 seniors from 16 seniors where order does not matter. And the number of ways the second selection could be made, where we have 15 juniors to select from, we're going to choose 2 of them, where order does not matter, would be 15 in combination with 2 here. Okay, so therefore, we're going to start to put this together. So therefore, the number of ways you can choose 4 seniors from 16 seniors would be 16 in combination with 4. That's the number of ways of making your first selection of seniors. Times, as we use the fundamental counting principle, the number of ways of making the second selection, that of being juniors, where we have 15 juniors to select from, and we need to select 2 of them where order does not matter, would be 15 in combination with 2. And so this would be what we need to do here. And now we just need to, go through and compute this here. And I would recommend that you just use your NCR function for these to speed things up. And so that's what I will do. So I'm getting 191,100 different ways of selecting 4 seniors and 2 juniors. Did anybody get that?
Yes.
All right, so there's a lot of different ways, and there's no way we'd want to sit here and enumerate all the possible ways. Our chance of getting them all correct would be virtually non-existent. All right, ladies and gentlemen, let's look at maybe one more here. Number 62. Now, in these problems here, we have to kind of decide whether a combination or permutation is relevant. And so if there's any hint where order matters at all, then we would be thinking permutation. If there is no hint whatsoever that order has any meaning or any importance, then we would be thinking combination. So number 62 here, it says how many different signals can be made using at least 3 different flags, if there are 5 different flags from which to select. Now, these are signals here, correct? So if we select, let's say we form a signal with 3 different flags. Okay, so let's say we choose, flag number 4, flag 3, and flag 2. Okay. This is flag 4, flag 3, and flag 2. Remember, there's 5 different flags. My question is this signal the same or different than this signal here? If I select flag 2, flag 3, and flag 4, are these the same signals or different signals? What would be your thinking? Do you think order matters here?
I think both would be different there.
Yeah. The order in which these flags are basically hoisted on a ship does make a difference, believe it or not. Okay. So like from top to bottom, order does matter. as to what flag goes, you know, top, middle, and bottom. So yeah, order does matter with these signals here. So order matters. Because order matters, we're thinking permutation here. And so ladies, I'm going to have you think about this and see if you can put this together using permutations. See if you can negotiate this one. And we're up to classwork number, I lost track. Just call it a classwork, all right? You'll just hand it in with all the other ones. All right, go ahead and try to do number 62. All right, so let's see if we can gonna address this last one here in this section. Trying to form a signal here with flags. And all right, and order does matter. Okay. Now we need to use at least 3 different flags. We have 5 different flags to select from. We need to use at least 3 different flags. So do you agree the word at least, the words at least 3 indicate that we could have a signal that could consist of 3 flags, or one that consists of 4 flags, or one that consists of 5 different flags? That's what at least 3 means. We have to account for all those. Okay. So that's something we need to understand. So therefore, we could have 3 flags, or we could have 4 different flags, or we could have 5 different flags. All right. Or means we're going to be what? We're going to be adding things together. All right. Now, how many different ways are there to form a signal with 3 different flags? If we have 5 different flags to choose from, but order matters. So now we're talking about 5 permuted 3 ways, or 3 at a time. This is a permutation because order matters, in which we select these 3 different flags from our 5 different flags. order makes a difference with our signal. Plus, or we could have 4 different flags in our signal. How many ways can we, from 5 different flags, select 4 different flags if order matters? That would be 5 permuted 4 ways. Plus, or if we could put together a signal that has 5 different flags, choosing from 5 different flags where order matters in which we select them or arrange them, then we would have 5 permuted 5 ways. So this is going to give you your answer when we get done doing this problem here. And so now we want to dial those up. So 5 permuted 3 ways is going to be 60 different ways of forming a 3 flag signal where all the flags are different. Or we have 5 permuted 4 ways, which is 120 different ways of forming a 4 different flag signal where order matters. Or 5 permuted 5 way. 5 permuted 5 ways, 120 here. So when you add these together, there would be 300 different flags or signals you could form that have at least 3 different flags. So there's 300 different signals you could form from 5 different flags if our signal is to have at least 3 different flags in it. And that's your answer, 300. Anybody get 300?
Yes.
All righty. All right, so let's see if we can now go to the PowerPoint 4.5. Oops, hold on a second here. And now, ladies and gentlemen, that we know how to count, or at least we might have a little better understanding of counting with combinations versus permutations versus the fundamental principle of counting. Let's try to put it together and wrap this up in computing probabilities, which would warrant our ability to enumerate the sample space of a particular probability. So section 4.5 is going to have us do that. And, best way to learn section 4.5 is by looking at some examples. Now, and I'm going to be honest with you, I'm not going to get really deep into some very heavy probabilities in section 4.5 because some can be some head scratchers. Okay. They can be very difficult to understand. My intention is that we are able to do some basic ones out of 4.5. All right. Because some of us might not even know, how a Keno game goes. I mean, has anybody ever played Keno? Well, I can attest, ladies and gentlemen, that I've never in my lifetime played the game of Keno. I've heard about it, but I've never played it. And because of that, I'm not going to ask you like questions involving some of these weird games that, I cannot sit here and assume that everybody knows how the game of Keno goes. Okay. So I'm not going to give you a question like that on Alex. Don't worry about that. I'm just going to give you kind of like a run-of-the-mill type questions. All right. Some pretty basic ones here. All right. But let's look at some examples and see if we can understand how some of these are going in this section here. Suppose we have a box that contains 20 light bulbs, exactly 4 of which are defective. Therefore, 16 are good. Make sense so far? 4 bad, 16 good light bulbs. If I take 5 bulbs out of the box, what is the probability that exactly 2 are defective? So if I randomly select, ladies and gentlemen, 5 of the 20 light bulbs from this box, we will assume that the light bulbs have been randomized, and so that any light bulb has an equal chance of being selected. So this constitutes a simple random sample. What is the probability that exactly 2 of them are bad? The 2 of the 5 I select are bad. Well, how many different ways can I select 5 light bulbs from 20 light bulbs, okay, if order does not matter? Well, that's going to be 20 in combination with 5. Now, if exactly 2 bulbs that I select are defective, I've chosen 2 of the 4 defective bulbs. Do you agree? Remember, there were only 4 bad bulbs in the box, or 16 good. I've chosen 2 of the 4 defective bulbs. And how many different ways can I choose 2 bad bulbs amongst 4 bad bulbs? Well, that's going to be 4 in combination with 2 ways. But ladies and gentlemen, if I select 2 bad bulbs, that means the other 3 bulbs, because I selected 5 bulbs, remember, the other 3 bulbs must be good. And there's 16 good bulbs in the box. So how many different ways can I select 3 good bulbs amongst 16 good bulbs if order does not matter? That's going to be in 16 in combination with 3 ways. So the fundamental counting rule says that the number of ways in which I can select exactly 2 bad bulbs and 3 good bulbs is going to be 4 in combination with 2 times 16 in combination with 3 different ways. And so, ladies and gentlemen, the probability of reaching into this box of 20 bulbs and selecting 5 bulbs and having exactly 2 of the 5 bulbs be bad is going to be equal to the total number of ways in which I can select 2 bad bulbs and 3 good bulbs, divided by the total number of ways that I can select 5 bulbs from 20 bulbs. We have to divide this now, okay? And to dial it up on the machine, to compute that probability of selecting exactly 2 bad bulbs, I'm going to use parentheses to help me out here. So I'm going to have open parenthesis 4 in combination with 2 times, okay, 16 in combination with 3 divided by the denominator, which is 20 in combination with 5. And that's how I dial it up on my calculator. Okay, hold on a second. Let me show you here. So this is how I dial up on a calculator. Ladies and gentlemen, notice I do enclose these inside parentheses so that I don't get any flack from the machine, okay, or get any logical error. Hit enter, and you get about 0.217. So there's about a 22% chance that if I reach into this box of 20 light bulbs that have been randomized, there's about a 22% chance that I'm going to select 2 bad bulbs and 3 good bulbs. Okay. Any questions about that problem there? Did that make any sense there at all? Just remember, with your probability, your bottom quantity has to be the total number of selections that are possible amongst all things. Okay. That's a common theme here. But that would be the probability of selecting exactly 2 bad bulbs when we select 5 bulbs from a box of 20 bulbs. Okay. All right, let's take a look at this one now. Probability of 4 of a kind. Suppose we draw 5 cards from a standard deck of cards. Of course, a standard deck has 4 suits: clubs, spades, hearts, and diamonds. And there's 13 cards per suit: ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. So there's 52 cards total. 4 times 13 is 52. Suppose we draw 5 cards from a deck. What is the probability that 4 of the cards are the same? 4 of the cards are the same. So later on, we reach into a deck and pull out 5 cards. What's the probability that 4 of the 5 cards we select are the same? Now, what does it mean for, these cards to be the same? What does that mean? 4 of the cards are the same. Same in what? Does it mean the same suit? Or does it mean the same? It says 1 for each rank. There are 13 ways of drawing 4 identical cards, 1 for each rank. from ace to king. So can somebody give me an example of what it means to draw 4 cards that are the same? Four cards that are the same.
I don't know, all the face cards.
Well, let's see. 4 cards have to be the same according to rank. My thinking, this is how I'm interpreting this here. You get 4 identical cards. 4 of a kind. My interpretation is that like we draw like 4 number 3 cards or 4 number 5 cards, or we draw 4 kings or 4 jacks or 4 queens or 4 aces. Is that a fair way to think about this or not? Now, why are there 13 ways of drawing 4 identical cards? 13 ways. Well, there's in each suit there are 13 cards, correct? So there's how many aces? There's 4 aces, correct? That's one way among the 13 suits that we could draw cards that are the same. They're all aces. Another way is that there are what? There's 4 twos, aren't there? Each for a different suit. We have 2 of hearts, 2 of diamonds, 2 of clubs, and 2 of spades. That would be another way of 13 ways of drawing 4 cards that are the same. Or we could draw like 4 kings. 4 of hearts, king of heart, king of diamond, king of club, king of spade. That's another way among the 13 different cards per suit that we could choose 4 of a kind. All right. So that's why there's 13 different ways of choosing 4 of a kind. Because in each suit, there's 13 cards, 13 different cards, different ranked cards. Okay. Times, but we're not choosing 4 cards. We're choosing 5 cards from the deck. So ladies and gentlemen, stop and think. If I choose 4 kings, a king of hearts, king of diamonds, king of spades, king of clubs, how many cards do I have left to choose for the 5th selection? If I keep all my kings out that I selected, I only got 48 cards left. Do you agree? With which to make one last selection, my 5th selection. So according to fundamental counting principle, we have 13 different ways of selecting 4 of a kind. Whether we select 4 twos or 4 threes or 4 fours or 4 fives or 4 sixes, 4 sevens, 4 eights, 4 nines, 4 tens, 4 jacks, 4 queens, 4 kings, 4 aces, times there's 48 different ways then of selecting the 5th card if we select 4 of a kind of whatever rank. So there'd be 624 different ways of selecting 4 of a kind. Everybody see this here? But ladies and gentlemen, we're trying to compute the probability of selecting 4 of a kind when we reach in and pull out 5 cards from a deck. So we need to divide the 624 by the total number of ways that we could select 5 cards from a 52 card deck, where order does not matter. So how many different ways can I select 5 cards from 52 cards if order does not matter? Well, that'll be, computed by using 52 in combination with 5, which is a very big number. 2,598,960 possible different ways of selecting 5 card hands from a deck of cards where order does not matter. Which means, ladies and gentlemen, therefore, to compute the probability of selecting 4 of a kind when we select a 5 card hand from a 52 card deck would be 624 divided by that big number there, at 2,598,960, which is a very small probability. If you move that decimal point 2 places to the right, that's only 2/100ths of 1% chance. 2/100ths of 1% chance of drawing 4 of a kind when you draw a 5 card hand from a 52 card deck. Okay. That would be the probability for that one there. All right, probability of drawing a full house. Cards again. We can similarly find the probability of a full house. What is a full house? I mean, if we don't even know what a full house is, this thing's dead on arrival. What's a full house? Well, it's a 5-card hand. That means we draw 5 cards from a deck with 3 of a kind and a different 2 of a kind. 3 of a kind and 2 different of a kind. So what would be an example of a full house hand? Well, do you agree I could select 3 kings, whatever suit they are, I don't care. I could select 3 kings, and I could select, let's say, 2 aces. 3 kings and 2 aces. Ladies and gentlemen, we call that a full house. 3 kings and 2 aces. Or we could select like, we could select 3 sevens and maybe 2 jacks. That's considered a full house. All right, so do we understand what a full house is? It's a 5-card hand where we select 3 of a kind and we select 2 different of a kind. Now, if we have 3 of a kind, it is made up of one of 13 ranks. Do you agree? In other words, there's 13 ranks per suit. There's a card that's ranked an ace. There's a card that's ranked 2. There's a card that's ranked 3. A card that's ranked 4. One that's ranked 5. One that's ranked 6. One that's ranked 7. One that's ranked 8. One that's ranked 9. One that's ranked 10. One that's a jack. One that's a queen. One that's a king. There's 13 different ranks per suit. So if we have 3 of a kind, it is made up of one of the 13 ranks and a choice of 3 of the 4 cards of that rank. Because remember, ladies and gentlemen, there is 4 cards for each rank because there's 4 suits. So each suit has 13 ranks. And there's 4 cards that could be selected that have the same rank as far as whether they're all 4 aces or 4 kings or 4 queens or 4 jacks or 4 8s or 9s or 10s or whatever. Okay. So how many different ways can I select? Okay. So how many different ways can I select 3 of a kind? Well, there's 13 different ranks to choose from. Times, ladies and gentlemen, how many different ways can I select from 4 of each rank, 3 of the ranks, where order does not matter? That'd be 4 in combination with 3. Because in other words, one of the possible ways of getting 3 of a kind is I could select a jack of clubs, a jack of spades, and a jack of hearts. Oh, but another way I could select that rank, the 3 of a kind of the same rank, is I could select a jack of diamonds, a jack of clubs, and a jack of hearts. Okay. So there's 13 different ranks per suit times there's 4 in combination with 3 different ways of selecting 3 of a kind from each rank. So that would give me 52 ways of selecting 3 of a kind. Now we calculate the number of 2 of a kind cards in a similar way. How many ways can we select 2 of a kind? Well, first we choose one of the 12 ranks that remain. Okay, why are there 12 ranks that remain? Because if we select 3 of a kind, ladies and gentlemen, of the same rank, let's say we select 3 jacks. Okay, well, that ranks out. We got to throw the jacks out as a rank. We can't select 2 more jacks. So we only have 12 more ranks to select 2 of a kind from them. Okay. So once we select 3 of a kind, That basically eliminates one of the ranks. And then we only have 12 ranks left to choose two of a kind. But how many ways can we choose two of a kind from 4 different cards of a particular rank? That'd be 4 in combination with 2. So there's 12 ranks to choose from after we choose 3 of a kind from one rank and keep that rank out, times a number of ways of choosing another rank, 2 of a kind from another rank would be 4 in combination with 2. So that's going to be 12 times 6, which is 72. So ladies and gentlemen, how many different ways can I choose 3 of a kind and 2 of a kind? That's going to be 52 times 72, which is 3,744 ways. Divided by what? Well, how many different 5-card hands can I choose from a 52-card deck? That's going to be 52 in combination with 5, which is the 2,598,960. So 3,744 divided by that big old number gives us 0.0014. That's the probability of selecting a full house, 3 of a kind and 2 of a kind. Okay. And like I said, some of these here, you may have to just think about them a little bit more in detail. Okay. And let them just kind of sink in your mind a little bit through over a little bit more time. All right. Think about them. All right. Well, let's see if we can maybe compute some basic probabilities here from 4 or 5. Like I said, I'm not going to give you really complicated ones, you know, like a game of Keno and all that stuff. And they're going to be kind of run of the mill, you know. So don't worry too much about 4.5. Don't let it like blow you out of the water. All right, I'm not going to give you too many complicated ones out of that section. Let's see, 4.5, because some of these, you know, can get a little bit off the beaten trail. And if we're not familiar with certain games, that can lead to a lot of consternation too. So let's just go to, looking at a couple of examples would also help in this section, 4.5. They do give you some other looks here. So ladies, I'm going to just look at this right here, okay? Example 450. This is in section 4.5. Examples can really give you different looks, and it only helps solidify your toolbox, if you will, or your understanding. Find the probability of getting 4 aces when 5 cards are drawn from an ordinary deck of cards. Hey, what if I gave you this question, ladies and gentlemen? We'll get back into this in a second. What if I said, what is the probability of selecting 5 aces when 5 cards are drawn from an ordinary deck of cards? You would say the answer is? If I said, what is the probability of selecting 5 aces from a deck of cards? You would say the answer is?
0.
0. There are not 5 aces in a deck. There's only 4 aces, correct? An ace of hearts, an ace of diamonds, ace of spades, ace of clubs. All right. But this probability is not 0. It says, find the probability of getting 4 aces when 5 cards are drawn from an ordinary deck of cards. All right. So do you agree that there are 52 in combination with 5 ways of drawing 5 cards from a deck of cards if order does not matter? That's the total number of ways, which is 2,598,960 different 5-card hands if order does not matter that you can draw from a deck. But ladies and gentlemen, there's only one way to draw 4 aces. There's only one way. That's if you draw all the aces. Ace of hearts, ace of diamonds, ace of clubs, and ace of spades. That really comes from 4 and being in combination with 4. But if I draw 4 aces, all the 4 aces out of the deck, that leaves me with 48 cards left from which to make my 5th selection. Remember, we're drawing 5 cards, not 4. So there's one way of drawing 4 aces times how many different ways of making that 5th draw from the deck, assuming we've drawn our 4 aces. Well, there's 48 other ways of making the 5th selection. So there's 48 different ways of what? Of getting 4 aces. when we draw 5 cards from a deck of cards. We just divide 48 by the big number and we get the probability. You can see the probability is very small. They leave it as a fraction, which you can obviously see that's very, very small. Okay. All right, here's a good one to look at. A box contains 24 integrated circuits, 4 of which are defective. That means how many are good? If 4 are bad, how many are good? 20 are good, correct? If 4 are sold at random, find the following probabilities. Suppose that of the 4 that we randomly sell, exactly 2 are defective. Well, how many defective ones we got? We got 4 defective ones, and we got 20 what? Good ones. And we're selling 4 of them. So, ladies and gentlemen, if exactly 2 of the 4 we sell are bad, then that means exactly 2 must be good. So the probability of computing if we sell 4 of these transistors here, or integrated circuits, the probability of selling 2 bad ones is going to be 4 in combination with 2. That's the number of ways of selling 2 bad integrated circuits from 4 bad ones. Order does not matter. Times, but we also sell what? 2 good ones. And there's 20 good ones to select from. So that'd be 20 in combination with 2 good ones. Divided by how many different ways can we sell 4 integrated circuits from 24? 24 in combination with 4. You get your probability. 190 over 1,771. What's the probability that when I sell 4 of these integrated circuits, none of them are bad? That means all 4 are good. Well, as I'm the probability of selecting all good integrated circuit boards would be, technically, it would be 4 in combination with 0, meaning we sell 0 bad boards of 4 bad ones, times 20 in combination with 4, meaning all the 4 boards we sell are good of the 20 good ones we have to select from. Divided by the total number of ways we could sell 4 boards from 24. That'd be your probability. What's the probability that all the 4 boards sold are bad, defective? Well, as we got 4 defective boards. So the number of ways you can sell all defective boards would be 1 way, right? If you just sell all the 4 bad ones. So that's going to be 1 way divided by how many different ways can you sell 4 boards from 24? Order doesn't matter. 10,626. So 1 divided by that would be the probability of selecting, or excuse me, of selling all bad boards. What's the probability of selling at least 1 bad board? Do you agree the probability of selling at least 1 bad board would be equal to the probability of selling 1 bad board, or selling 2 bad boards, or selling 3 bad boards, or selling 4 bad boards? But ladies and gentlemen, there's an easier way to compute that probability. What's the complementary event to saying that we sell at least 1 defective board? What's the complementary event of at least 1 defective board? The complementary event of selling at least 1 defective board is to say we sell no defective boards. Well, we already computed that probability. The probability of selecting selling no defective boards is 1615 over 3542. We're going to subtract that from 1. And you now have the probability of selling at least 1 defective board. Okay. All right. A student needs to select 2 topics to write 2 term papers for a course. There are 8 topics in economics, 11 topics in science. Find the probability that the student selects 1 topic in economics and 1 topic in science to complete the assignment. All right. Now we're going to select 2 topics. 1 has to be what? From economics, and 1 has to be from science. Well, we have 8 topics in economics. So how many different ways can I select 1 topic from economics from 8 economic topics? If order doesn't matter, that'll be 8 in combination with 1. Times, but ladies and gentlemen, I must also select 1 topic from what? Science. And we have 11 science topics to choose from. So that'll be times 11 in combination with 1 ways of selecting 1 science topic from 11 if order doesn't matter. divided by, now how many different ways can I select two topics from, how many total papers, excuse me, how many total topics? That'd be 9 plus 11, or what, 19 total topics to select two from. That'd be 19 in combination with 2. By dividing the numerator by the denominator, you come up with a probability of selecting a topic in economics and one topic from economics and one topic from science. About a 51.5% chance. Okay. So, ladies and gentlemen, this is the key. The type of problems that I'm going to assign out of section 4.5 are basically going to be embodied in these examples: 4-50, 4-51, 4-52. These are fair game questions that I could ask you and Alex. Okay, fair game. These are the types that I will ask you. There's some other problems in this section that I'm not going to ask you. Some problems as far as like, especially like for a game of Keno or something like that. I'm not going to ask you one like that. They're going to be pretty straightforward. So what I would recommend you do is study over, if you will, these examples that I went over in section 4.5. That's going to help immensely. All right. And you might want to do also some fair game problems out of your textbook for section 4 or 5. Would be, these are problems that you also want to try to do. These are fair game. Number 1 in your textbook. Number 3, and you do have answers to these in the back of your textbook. Okay. These are all fair game problems here. So 1 and 3. And number 5. Those are all fair game problems. 1, 3, and 5. Okay. And also number 9. So these are problems that, you know, you want to try to do in your textbook. They do have the answers to these problems in the back of your book. And I don't know, I'll see if I can maybe, I might be able to throw together a real small video showing you how to do these problems. Okay, and I'll put it on Canvas. All right, I'll try to work these out here. All right, ladies and gentlemen, that is it. Gotta go. I will try to open up all this stuff that I have to open up on Alex ASAP. And just note the due dates on that and just kind of keep those in your mind so we don't get behind the old 8 ball. Okay. All right. I'll be on the line for a couple minutes if there's any questions or comments. If not, have a great day.